All right. Good morning, everybody. So, we are Team Ratchet doing our FIP on medical image report generation. Our supervisors are Dr. Tanuja Ambeguda and Professor Dulani Meedani. So, this is next slide. So, this is a presentation outline. And let me begin with giving you some introduction. First, in the medical field, there are different types of medical imaging, such as MRI, CT, and X-rays. And there is a special doctor called radiologist who is responsible for analyzing these medical images and writing accurate reports. So these medical reports will be used by other doctors to identify various anomalies in human internal lungs. So this manual process of medical report writing can be time-consuming task that requires experienced radiologists to do the job efficiently. With this, we have identified several issues. With the realm of medical imaging, the manual process of report writing can be subjected to various issues, including delays, inaccuracies, and errors. So such errors can result in serious consequences, including potential facial harm or maybe even death. So therefore, it is imperative to address these issues and improve patient outcome by exploring more efficient and accurate methods for medical report writing. And so we are doing this because the current methods used to generate medical reports are not fully addressing the problem. And there is a need for a new approach that can improve the accuracy and efficiency of the process, ultimately benefiting the patients. And how we are doing this? So this is where advanced technologies such as machine learning and transformers can play a vital role in automating the process of medical image analysis and report writing. So ultimately leading to improved accuracy and reduced risk. Additionally, we are using explainability techniques, which will allow us to better understand the reasoning behind the automatically generated reports. So next, here we have shown survey conducted for the Journal of Medical Error Reduction and Prevention, which is published in the website of National Library of Medicine, which is an official website of US government. So from this survey, we can clearly see the need of automated tools. So in here, you can see like 52% agreed the medical error happened since they didn't have enough experience and so on. So all those errors happened since those processes are manual done by humans. So what motivated us for doing this FIP in this scope? So as I mentioned before, the manual process of medical image report generation can have delays, inaccuracies, and errors, which can result in serious consequences, even death. So, and also for manual chest X-ray report writing, it requires well-trained and qualified medical experts like radiologists. So it's a critical issue for hospitals, mostly in rural areas, to find a radiologist in emergency cases. So as an example, all three of us are from Bandar area, and even in Bandar Hospital, there are no radiologists available. And so from a well-trained automated report generation framework, we can mitigate the above mentioned two issues. So it motivated us to develop a fully featured automated chest X-ray report generation system. And also, furthermore, only few existing studies for X-ray report generation are using the state-of-the-art deep learning techniques. And we will discuss the limitations in existing literature in upcoming slides. And also, automated chest X-ray report generation framework can be used by medical professionals as well as a learning tool for medical students. So in this slide, we have shown how the X-rays are used to diagnose anomalies. Chest X-rays can reveal areas of opacity, and radiologists, they use the opacity level in the chest X-ray to identify the and localize various anomalies in the chest. So in the right side image, we have highlighted the area in red where we can see the opacity difference. Next. So this is the simplest overview of our proposed framework. So users, they can input a chest X-ray image to our framework and it will automatically generate an accurate report for you. So in this slide, we have shown an example report generated for a normal and pneumonia chest X-ray image. So in this slide, we have shown 4 chest X-ray images, and the true text mean the report that is there in the dataset, and the predicted test is the predicted test from our model. So from this, we can clearly see that most of the medical terminologies presented in the true text is there in the predicted test. So from here, we can clearly see that automated tool can be trained to accurately generate medical reports for chest X-rays. And these are the objectives for our study. So we have explored related literature and designed an automated solution for manual process to replace the manual process. And we have developed a suitable model with explainability, and we have evaluated the model performance with real world data. So next, the output is output of our system is a system which takes chest X-ray as an input and output a well-explained medical report containing relevant medical terminologies. And outcome of this uh, outcome of this research is a transform-based deep learning model to automatically generate report for chest X-ray images with high accuracy. Next, we will look at some related studies. Next slide. Yeah, so this is a small comparison of related studies more relevant to our study on medical image report writing, and each of them, they are using different techniques to generate reports. And next, this is the next, next slide. So this is the Ratchet paper. So we have referred this study in the slide as the base model of our system. In their implementation, they have used DenseNet 121 CNN encoder for feature extraction and a transformer with multi-head attention as a decoder to generate the report. And they have used Mimic CXR dataset to train, test, and validate their results. And the accuracies obtained are shown in the slide. Yeah. So these are the limitations of the existing literature. So for feature extraction of the images is done by using NN models usually. So CNN models are more into capturing only the local features of the image. And also there is a lack of explainability models available for chest X-ray report generation. Also, most of the uh, related studies are focusing on like improving the visual extraction part. Like they are not like focusing on visual extraction part. They are more focusing on the report generation part, which means the decoder. And there are no publicly available deployed product for chest X-ray report generation, which can be used in real clinical setting. There are few products for image classification, but we were not able to find any product which are publicly available and deployed for report generation. And there are no studies found which are approved by medical professionals for chest X-ray report generation in the domain. And next slide. Okay, so next we are going to explore some data sets that we have used and available in this domain. Yeah, so this is the ROCO dataset. It contains 82K medical images, but it's not only chest X-ray images. It contains all the medical image types, including CT, ultrasound, X-ray, and many more. And the Medicat dataset, it contained 270K images, and this dataset was created by combining the ROCO and IU X-ray datasets, and it has manually annotated reports. And this is IU X-ray dataset, and we have used this dataset for our research. So it contains 7,471 X-ray images with their corresponding reports, and it has all lateral and frontal images. And for our study, we are only considering frontal images of the frontal images. And this is the Mimic CXR dataset, and we will discuss it more in the next slide. So Mimic CXR, it's the largest available dataset for CXR images, and it contains around 377K X-ray images with reports. And we have chose Mimic CXR dataset to be used to train our models. Therefore, in Mimic dataset, there are two versions available. One is large resolution DCOM image version and low resolution JPEG version. So for our study, we are using the low resolution JPEG version because the large one is like hard to handle because of its size. And in Mimic XR, we can see manually labeled, the images are manually labeled to 14 categories using Chestxpert labeler. And also the reports in this data set were reviewed by a board certified radiologist, they have like 8 years of experience. Yeah, and next. Yeah, so this is a CXL-SEC dataset. So CXL-SEC is a segmented chest X-ray dataset introduced by our team, and it is an extended version of previously discussed Mimic CXR JPEG dataset. So in CXL-SEC, we have around 243K segmented frontal images, and it is only 4.24 GB large, so which is smaller than the Mimic CXR dataset. And we have changed the split ratio to 80 to 10 to 10, randomly splitting the images. And for image segmentation in this dataset, we have used SA unit model, which is already existing. So currently we have published the dataset in Fish unit. Yeah, next I would invite Mahila to continue the presentation.
Thank you, Kasun. So here are the novelties of our research. First one is the comparative analysis of using different CNN models for the feature extraction. After that, we have used a vision transformer and a CNN as a feature extractors to preserve global and local features, since it is an unexplored area for the domain. Also, using the extracted features, we have implemented explainability, which helps to improve the trust of the person who uses our system. Also, we have explored the generalizability and transfer learning of the model using Mimic CXR and IU X-ray datasets. And finally, we have deployed our product as a web framework, which can be used in a real clinical setting. Next slide. So now let's move into our system overview. In this section, I will go through the concepts that we have used in our medical image captioning model. So this is a high-level overview of the base transformer, which we have used to refer to build our model. It mainly consists of embedding layer, positional encoder, and a multi-head attention layer. So let's go through each one of them to understand a little bit about them. So one of the key concepts that we have used in our implementation is attention mechanism, which can selectively focus on specific parts of the input data. In our case, it is chest X-rays and medical reports. Mainly, there are two types of attention. One is simple attention and other one is self-attention. So in simple attention, it selectively focuses on words which expected to some external query, as in this first example. The other type of attention is self-attention, which consider the relationship among the words within the same sentence. So what it does is it tries to understand the words according to their context. So next slide. So another two main concepts in the transformer is embedding layer and positional encoding. In the embedding layer, words are converted into the meaningful vectors, and it works as a kind of a lookup table to get learn vector for each word. So to understand this, we can use these given examples. And the next important thing is positional encoding. It is used to incorporate the positional information of the input sequence into the model by adding fixed size of vector to represent the position of each token. So we can understand it by using this example. As you can see, the word not completely changes the meaning of these two sentences. Next slide. So next thing is attention net, which is also another important component in transformer. This is where the attention is calculated, and there are multiple attention heads in the model. The reason for having multiple attention heads is to allow the model to attend different parts of the input sequence simultaneously. So this allows the model to capture the different aspects of input, improving its ability to learn and generalize. In our case, different parts of the image and the chest X-ray report. So here is an overview of the attention net. The attention is calculated by using this given equation. And in our system, we have used 8 attention heads. So we can further understand this by using this visual example. Here, this shows the process of how one attention head works. But as I said, there are in our model, there are multiple attention heads, which focuses on multiple parts in the input, in the image or given input. So in this component, attention matrix is calculated, and it is later multiplied with the original value to get the focus part in the each input. So we can understand this better from this chest X-ray images. The first image works as an attention matrix, and using that matrix, this filtered part is generated with one attention head and pass it to the decoder as the extracted feature. So there are multiple attention heads, as I mentioned earlier, which helps us to focus on multiple parts in the image. So this is the architecture of the vision transformer, which is kind of similar to the original transformer and uses the same concepts as I discussed. The main difference in here is it can process images and identify the context of the image. Once we input the image, we split into the small parts and encode with their position to each part of the image and pass it to a multi-head attention layer to process it. We have used this as a feature extractor in our model, and we will discuss about this later. And this is a convolutional neural network, which is also a concept that we have used for feature extraction. The first layer of CNN performs a process called convolution. it looks for smaller patterns or features like edges, corners, or uh, corners that are present in the image. As you can see, it does this by sliding a small window called kernel across the image. This process helps the network to detect basic shapes and structures. Next, we have the pooling layer. It is job of pooling layer is to reduce the dimension of the features extracted by the convolution layers. This process makes the model more manageable and efficient. After several convolutional and pooling layers, we can get those features out of the model, or we can use a fully connected dense layer to do a classification task as we need. Next slide. So those are the main concepts that we have used in our approach. So from here, I will go through our methodology. We have done our research in 3 phases in an incremental way. In each phase, we have implemented new scenarios which help us to cover the existing literature limitations. So before going into each phase, I will first go through the pre-processing techniques and hyperparameters that we have used in our model. So these are the pre-processing techniques we have used. We have used techniques like resizing, flipping, applying random brightness before the training. These techniques helped us in achieving consistent image quality across the different chest X-rays, generalize the model across large range of images, and also to reduce the unwanted noise present in the images. Next slide. So these are the hyperparameters that we have used during our training. For the encoder, it took like 2.5 days to train the model, and for the overall model, it took around 5 days. So let's move into the each phase that I mentioned earlier in the beginning. So our model mainly consists of an encoder and a decoder. In the encoder, what we are doing is we are extracting the feature part, and in the decoder, we are doing the report generation part. So in the first phase, what we have done is we did a comparative analysis between these CNN models to find the best feature extractor for our model. Out of these CNN models, we were able to find out that ResNet 101 performs better than the other CNN models for our task. So we used it with segmented images to implement the explainability and report generation model with the help of transformer decoder. For the segmented images, we have used our CXL dataset that Kasun mentioned earlier. Next slide. And in the second phase, we have extended our model by using pre-trained vision transformer for the feature extraction. The reason for using a VIT is unlike traditional CNN models, which rely on convolutions to extract features. Vision transformers use self-attention mechanism to capture the relationship between all the different pixels in the image, which enables the model to capturing better details in the image. I will explain how the whole model works in the next slide. So next. So this is our final. So this is our final phase where we have used the both vision transformer and CNN to extract features from the image, and this. Vimukti, can you go to the next slide? Hello.
Can you see the screen?
Yeah. Can you go to the overall model slide?
So this is the overall one. Can you like see? So this is the final one.
We are in the phase 2.
Okay,
Can you
maybe
go to phase 3?
is somewhat bad. So can you hear me?
Yeah, now I can see this.
Okay.
So this is our final phase where we have used the both vision transformer and CNN to extract features from the image, and this is the overall architecture. So first I will explain how the whole model works. So what we have done is at the input, we extracted features from both vision transformer and the CNN, then concatenated features using the global local fusion network. After that, we passed that extracted features into the decoder. So in the decoder, reports are takes as the input, and they are converted into the vectors and stamp their positions. Then those vectors are passed into the first multi-head attention layer. As you can see, there are 2 multi-head attention layers in the decoder. In the first multi-head attention layer, it understands the context of the input medical reports and then pass them into the second multi-head attention layer. So this is where the mapping happens between extracted features and the reports from the first multi-head attention layer. So after this mapping, output of the second multi-head attention layer goes through the feed-forward linear and the softmax layers. At the end of the model, it will pick the word which has the highest probability and concatenate it with the already generated report. This process will happen until the end token is generated. Also, with the use of CNN output, we are generating a prediction for each image and a GradCam, which shows the focus area for that disease prediction. And with the help of extracted features and the predicted tokens, we are generating explainability, which we will discuss later in our presentation. So the main part in our research is using VIT and CNN to preserve local and global features of the image. The reason for using both CNN and vision transformer is CNNs are better for their ability to capture local features in an image. With the help of convolution layers, CNNs are excelled at detecting patterns, edges, textures, and like local structures within an image. On the other hand, vision transformers are designed to capture global features by leveraging its self-attention mechanism. So unlike CNNs, which process input images kind of like a hierarchical way, VIT divide image into the small patches and process them independently. Also, by incorporating self-attention layers, VIT models can learn global relationship between patches, enabling them to capture long-term dependencies. So using both these models together improved our model significantly. Next slide. So these are the evaluation metrics that we have used for our classification task. We have used accuracy, which tells how well our model predict the correct output, sensitivity, which measures the ability of the model to correctly identify positive cases, and finally, the specificity, which measures the ability of the model to correctly identify negative cases. Next one. Can you go to the... Yeah. These are the So these are the evaluation matrices we have used for generated reports, and they are widely used in natural language processing domain. So mainly there are 4 matrices, namely Blue score, CIDR, RUG, and Meteor scores have been used to evaluate our generated reports. So from here onwards, Vimukti will go through our explainability approach and the results. Thank you.
Okay, Mahela, can you hear me?
Yeah. Yes.
Yeah, so okay, now let's move into the explainability interpretation of the classification. So we have used a GradCam saliency maps for interpreting the classification results. Specifically, we have used the last convolution layer of the CNN to generate the heat map. So as you can see, we have shown GradCams generated for 2 chest X-rays of the classes cardiomegaly and the pleural effusion. So regarding the explainability of the model, attention maps is used to directly, so currently to depict the where the model predicts in the input image for each word that it is generating. So similar to us who build the representation of a whole scene by focusing on the relevant parts of the scene at different times dynamically. So the model also focuses on different parts of the image when predicting the words of the report. So the model selectively attend to different parts of the input image, or in our case, the chest X-ray, giving more weight to certain parts that are more relevant to the task at hand, or in our case, the word which is generated. So so currently we have used the attention mechanism to do the model explainability. So this attention map includes where the model focuses on the input image for each word. The attention weight from the second multi-head attention modules is used for this. So this slide contains an example situation where the chest X-ray in the right side. Kasun, can you see this screen?
Yeah, now we
sometimes go to another slide. Can you like close it and come to presentation mode? Okay.
Can you see the screen?
Yeah.
Yeah.
Yeah, sorry for that. Yeah, so this slide contain an example situation where the chest X-ray in the right side of the slide is input and into the model, and the report is generated. So sentence wise, we can get an understanding where the model focuses to predict the sentence. For example, in this set of images, we are predicting the sentence enlargement of the heart. We can see the model focus on the cardiac or the middle region of the image. So also here you can see the input image, a device is attached as you can see to the right lung, it is also highlighted as a white block in the input image. So this is below a set of image.
1 minute, Professor Chatura got disconnected, I think.
Okay. Okay. So yeah, also, so in the framework, we have even used the color maps to improve the visual interpretation, similar to what we are seeing in this slide. So, okay, now let's move into the results section. So, so these are the results of the initial comparative analysis that we have done using different CNNs for visual feature extraction. So this was the first attempt to improve the encoder. According to that, as you can see, the ResNet has better values to compare to the other models. And then for the image segmentation part, which we have done for the further improvements of the model, we've used several unit variants, namely the vanilla unit, unit plus plus, attention unit, and the SA unit. So we got better results from the SA unit, and because of that, we have used it for segmentation of the input images. And moving forward, so we have created our own dataset called CXL-SEC using the SA unit model, which performed better in the earlier stage. So we have done a medical image classification task using both the Mimic CXR and the CXL-SEC dataset, and to find out like the which performs better. So as you can see, our dataset, which is the CXL-SEC dataset, actually gives better results compared to the original Mimic CXR dataset. So these are the overall results of our research. So since we have done the research according to the several phases, results for each phase is shown in the table. So in this phase 1, we have trained the base model with the base results of the model of comparative analysis. Next, combining all these, in the phase 2, we have trained the model which uses vision transformer in the encoder and the text transformer and the CXL-SEC dataset. So according to that, we got really good results compared to the base model. And finally, in the phase 3, for all the experiments which we have done, we have decided to create a model that preserves both the global and local features of the chest X-rays, and which is kind of a noticing limitation in almost all the research works that around this area. So the results of the model actually surpasses all the previous models, and we have achieved a state-of-the-art results compared to the models which uses transformers in the encoder. So this model is what we are calling as the Chestxpert model, and pave was the way to create an amazing framework which we show lately. And to evaluate the generalizability and transfer learning capabilities of our model, we have trained the model with Mimic CXR and IU X-ray dataset. So for model generalizability, we have trained the model with Mimic CXR and IU X-ray separately and tested each model with both the Mimic CXR test dataset and IU X-ray test dataset. So results were surprisingly and like they ultimately proved the point that our model is generalizable, and also doing transfer learning yielded better results for our model. So first, we have actually trained the model with Mimic CXR, and using the pre-trained weights of Mimic CXR, we have again trained it with the UX-ray, and the results were also improved. And so let's move into the final section of our presentation, which is the verification of the results using real-world medical professionals. So this has been done to verify the things like the correctness, reliability, the usability, efficiency, and like integrity of the our framework and the results. So these are the users who participate for our study. So 3 radiologists from the Etala and Badul hospitals, so 7 medical doctors from the Etala, Bandra and Badul hospitals, and 10 medical students from different state universities. So among them, about actually 40% of users have 5+ years of experience in the radiology domain, and also 25% of them are professionals in this field. So these are the results of the system usability study that we have done to assess the usability of our created framework. So according to the results, users found it kind of very easy and convenient to use the system. So as you can see from this slide, actually about 50% of the mention that the system is somewhat complex, and because of that, we have added a new user manual to the framework, which will show in the demo. So these are the results of the report generated by the framework, and according to the user feedback, the generated reports have overall accuracy of 87.75. So these are the results of the explainability attention maps generated by the framework, and according to the user feedback, the generated attention maps have an overall accuracy of 76%. And moving forward, before ending the presentation, we will highlight some key achievements that we have received. So we have published 2 research papers, one in the ICRC conference in Sabaragama University, and the other one in the International Conference on Cyber Management and Engineering in Thailand. So also we have published our segmented dataset in Visionet website. And finally, by presenting our final year project, we have won a hackathon named IntelliHack, kind of a machine learning hackathon organized by the University of Colombo School of Computing. And yeah, so this is the we'll move into the demo now.